All right, welcome again to Advanced Modeling Methods. And this will be lecture number 15. Okay, and so far we've implemented the boundary element method for the solution of potential problems. Potential problems, remember, are those governed by the Laplace equation. One of them is heat conduction. Steady, no generation, homogeneous heat conduction. On a homogeneous media, that is. So, well, we notice, or we implemented BEM, we notice how relatively easy it would be to implement, how powerful it would be. How easy is the user interaction. Basically, you only have to worry about discretizing the boundary of the problem. You don't have to worry about meshing the interior like in finite elements. And how accurate it is, because it produces solutions that are orders of magnitude more accurate than anything else that we've done up until this point. But the drawback is, well, we've done it for potential problems, for the Laplace equation. Would it work for other problems? Okay, and the answer to that is maybe. Maybe, depending on the type of problem, we should be able to implement the concepts of BEM as we've learned it so far. There might be some kind of hand waving that we need to do. There might be some kind of adaptation that we need to implement to make it work. But there are a number of fundamental solutions for the different types of problems. Okay, like say for example the Helmholtz equation. Helmholtz equation is another type of equation that governs another class of problems. Usually, for example, when you talk about wave-like problems like acoustics or vibrations, and you transform them to the frequency domain instead of the time domain, you end up with an equation in space that looks sort of like it has a Laplace, and then it has a coefficient multiplying the dependent variable. That's called the Helmholtz equation. Now, the Helmholtz equation has its own. You can implement boundary element. You can construct a boundary integral equation. You can discretize the boundary integral equation, but the fundamental solution is going to be completely different. It's not going to be the log of R. It's going to be associated with R, but it's going to be, sometimes it ends up being functions of Bessel functions and things like that. So every single problem or every single governing equation has its own fundamental solution. And remember, a fundamental solution is nothing more than the governing equation you have, but with no field. There's no geometry, it's a free space solution, and it's a response of putting a source at any point xi. If you put a source at any point xi, what is the answer, what is the response that you get out of this equation when there's no field, when there's no geometry, when there's no boundaries, okay? Now, we're gonna stick with heat conduction, but we're gonna add a little complication to the problem. And one of them is, well, what happens when you have internal heat generation, when you have a non-homogeneous term in the equation? And can we handle that with boundary elements? And yes, there's some things that we're going to need to do, but this is a typical case where, well, we are going to end up using the same fundamental solution because the equation is the same. Okay, it's the Laplace of the temperature, but now it's not equal to 0, it is equal to something, because something is actually forcing the governing equation to produce something. Something is producing energy or absorbing energy within the field. So let's talk about the BEM implementation for the Poisson equation. The Poisson equation is essentially the Laplace equation. For example, we talk about steady heat conduction with energy generation. So the Poisson equation is simply the same thing as the Laplace equation, but it has a non-homogeneous term. Notice that it's not a non-homogeneous medium. What I'm talking about, non-homogeneous medium would mean that the conductivity changes as a function of position. This is not the case. This is basically saying that the equation is non-homogeneous. This makes it non-homogeneous. This basically makes the Laplace not equal to 0. So where UG triple prime of X is a space dependent energy generation per unit time. That's why there's that dot per unit volume. That's why there's that triple prime. That means that the units of these are watts per meter cubed, and SI units. Energy per unit time is power, watts, and per unit volume is meter cubed. That makes all of these dimensionally consistent. So we call this the Poisson equation, and remember again, the Poisson equation is nothing more than Laplace equation equals to non-zero. All right, so now consider the general form. It's general form. Laplace of t is equal to minus b of x. And that b of x contains the generation and it contains the conductivity. And we know the units of b. By the way, what are the units of b?
Same as
Temperature? What are the units of the Laplace? It's derivative with respect to x squared. So it's x squared, it's meter squared, right? That's the units of the Laplace. So this gotta be Kelvin per meter squared for these to be dimensionally consistent. And you can actually get it directly from here. UG is watts per meter cubed. Well, K, the conductivity, is watts per meter Kelvin, right? So the watts and the watts go away, the meter cube and the meter go to meter square, and the Kelvin goes to the top, right? You can get it from there. All right, so such that B of X is equal to minus UG triple prime over K. All right, and when I say a function of X, remember that I'm embedding the entire coordinate system in there, whether it is X, XY, or XYZ, it's all embedded into X. I just don't want to write the whole thing, I want to make it general. All right, so I'm going to follow the same process that I did for multiply by g of x and xi, the Green's function, and integrate over omega. So we'll have the integral over omega of the Laplace of t times g of x and xi. The omega is equal to minus the integral of b of x, g of x and xi. Now keep in mind, throughout all this that I'm going to do now, that b is known, all right? Whatever it is, it can be a function of x, xy, xyz, it doesn't matter, it can be a constant, but it's known. We know what it is, because it's part of the governing equation. For a problem to be solvable to start with, we will post, the geometry needs to be known, the boundary conditions need to be known, and we'll post, and the governing equation needs to be completely known. That means that whatever term in there, including this one, needs to be completely defined. All right? So, remember what we did to this function, to this integral on the left hand side? We applied integration by parts twice, which is Green's first identity, right? Twice. Apply Green's, and we're going to call it second identity to left hand side. And that would be the integral flip the signs right here. Okay, so I'm gonna do this. I'm gonna do t of x, then Laplace of g of x and psi, the omega, and then this will be minus the integral over these of t of x dg dn, then we have plus the integral over gamma of g of x and psi, the tdn of x is equal to minus the integral of b of x, g of x and psi, the omega. So notice that I haven't done anything to the right hand side. And everything that I've done to the left hand side is the same that I did before to the Laplace equation. Same thing. Alright? Now let this be equal to minus the Dirac delta function at the source point psi. This is standard. This is what we did during the first lecture of boundary elements. So leading to G being the Green's free space or fundamental solution. The same one that we've been working with, such that g of x and psi is equal to minus 1 over 2 pi log of r in 2D. For instance, same function that we've been using, such that r is equal to the square root of x minus xi squared plus y minus yi squared. Also let q of x be equal to the TDN, and let h of x and psi be equal to the GDN of x and psi. So this results in the BIE, boundary integral equation. That means that C of psi, T of psi, plus, and I'm flipping the signs as you can see, because of the negative here, I'm flipping all the signs, the integral, and this would be T of x, h of x and psi, is equal to the integral of q of x times g of x and psi plus b of x, g of x and psi d omega. All right, so this is identical as our previous boundary integral equation, except for this term right here. This one didn't exist before. Okay? Now, What do you notice about this boundary integral equation that stands out of its name? Boundary integral equation. It means that there's boundary integrals, right? There's one boundary integral, there's another boundary integral, but this is not really a boundary integral, that's a domain integral. Okay? So we cannot really call it a boundary integral equation because there's a domain integral. Notice that this is not truly a BIE because there remains a domain integral. So, however, the integrand, that is b of x or v of x times g of x xi, is completely known. Right? So therefore, so that b of x, g of x, and xi, unlike this integral where we don't know the temperature, we don't know the flux, that's what we're trying to solve for because we're trying to solve the heat conduction problem, that integral is fully known. Okay? All we have to do is solve it, which might not be trivial, but we know that there's an answer to it. So let b of xi be equals to this integral over the domain of b of x, g of x, and xi dl. It is a function of xi because x goes away in this integration. This is the domain of x, right? It's like integrating from one limit to another if this was a 1D integral. Okay, the only thing that remains in that integration process is the dependency xi. So wherever you locate the Green's function, wherever you position the source point of the Green's function, you're going to have a different answer, and that's what we call this b of xi. Now that integral is fully known. We can solve it. That's why I'm just going to call it b. Right? Now the problem is how to solve it. And I'm going to table this for a little bit. I'm just going to frame this, and I'm going to say, note, it may not be trivial to solve this integral. Okay, but table it for now. Keep in mind that we have to find a way of solving that integral. And what we have is that the BIE becomes C of xi, T of xi, plus the integral of T of x, H of x and xi, the integral of Q times G of x and xi, plus B of xi. Now, discretizing into n boundary elements, and let's assume for now where T and Q are assumed to be constant along each element, leads to C of psi, T of psi, plus the summation from j equal 1 to n of Tj and Hij, the let's not call this hij, sorry. Let's just call it integral over delta gamma j of x and xi is equal to the summation from j equal 1 to n of qj, the integral of g x xi plus b xi. That's a discretized boundary integral equation. This is the discretized version of these. And collocating the source point xi at the center of each boundary element such that xi I is such that I goes from 1 through n. Leads to Ci, Ti plus the summation from j equal 1 to n of Tj, Hij is equal to the summation from j equal 1 to n, I'm going to put a hat on this one, of Qj, Gij plus Bi. Alright? And we know what these are. Hij hat is equal to the integral over delta gamma j of h of x psi I d gamma. Gij is equal to the integral over delta gamma j of gx psi I d gamma. And Bi is equal to b of psi I, which is equal to the integral over the domain of b x g of x and psi I d omega. Alright? So again, we're going to combine these with these. Alright, so we're going to let Hij be equal to Hij hat plus Ci times the Kronecker delta times the identity matrix. So you're just basically going to add Ci to the diagonals of H hat. So then we have, let me see what nomenclature I use here. Alright, so I'm going to have summation from j equal 1 to n of Tj, Hij is equal to summation from j equal 1 to n of Qj, Gij plus Bi such that I goes from 1 to n as well. And therefore, in matrix vector form, notice that this is just simply H times a vector T is equal to G times a vector Q plus a vector B. This one is of size n by n, this one is of size n by 1, this one is of size n by n by 1, and this is of size n by 1. So the existence of a non-homogeneous term in the governing equation just basically adds a vector to the system. So notice or note that the existence of a non-homogeneous term in the governing equation, or simply in this case b of x, or minus b of x, that's what's on the right hand side of the governing equation, simply adds a vector, and let's call it a known vector, to the system of equations. And that is that not known vector, is that vector b, which is known. I'm going to call the known vector b to the system of equations. All right? So after rearrangement of the system with boundary conditions, what do we end up with? A times x, where that vector x is what we're looking for, contains some t's and some q's. Is basically what we don't know, the part of the boundary that we don't know, is equal to some matrix B times the vector of boundary conditions, which is known. This is not known. A and B contains pieces of H and G, plus the vector B. The dimensions have not been altered. It's all n by n and n by 1. So, since all of these is known on the right hand side, basically this leads to a system A times x is equal to some, we're going to call it D, which we can solve by LU decomposition or Gaussian elimination or whatever method we want to use. In the Fortran code, we use LU decomposition. In the MathCAD code, internally, the MathCAD code uses a version of Gauss-Seidel, kind of an iterative solver for these. All right. So, solve for x. And that's it. So nothing has changed in the mechanics of the code. So if you think about it, the code has to have the same structure. All we need to do is include a routine that generates that vector b, which will then be added to this vector. Remember, this matrix times this is a vector to form the right-hand side known vector of the system. So we need to form the vector b. Okay. Now, how do we obtain the vector b, whose elements are, so the elements of vector b are bi, which are equal to b as I, which is basically the integral of bx, g of x and xi, I, d. All right? How do we do that? For any source point that we pick, we have to perform that integral. So this involves a domain integration process. Okay, in general, it may be solved using cell integration. All right, so basically a cell integration would mean that if this is a domain, we're going to break out this domain into cells, kind of triangularize it or polygonalize it. Something like this, where each of these is a delta omega, I'm going to call it K. Delta omega K. Where the domain omega is equal to the summation from K equal 1 to number of cells of delta gamma K. So that's how we solve a domain integral. We have to break up the domain into pieces and then assume some sort of local integration or assume some sort of local expansion for the function in terms of basis functions or shape functions. So expand the integrand dx g of x by I locally on delta gamma K in terms of multidimensional shape functions. Like polynomials, for example. And then create multidimensional shape functions, well, in multidimensional Jacobians. And so on. All right? So this is in general how you would do this. But this is not the way that you should do this. This is a wrong way of doing things. Why? Well, because this is domain integration and this is boundary element methods. We should avoid having to do domain. This is now we're going into the realm of finite elements or finite volumes. So why would we call a method boundary element when we're going into the interior? Right? So this completely detracts from the very nature of boundary elements. A lot of people do this, and even for more complicated governing equations, more complicated problems, they go into the interior and then go through all these hand waving and approximations and shaping of the function and the integrand to integrate it in space. But why don't you use finite elements? Well, you have to go through all the trouble of coming up with fundamental solutions, integrating these fundamental solutions in space, on the boundary, then having to deal with singularities, which none of the other methods have to deal with, and let's go to the interior. Why go through the trouble of all these when you just use finite elements or finite volume? So let's just write that down. Why go through the trouble of discretizing the interior in a BM implementation when we could have used cell integration and interior discretization in general for BEM implementation is undesirable. Undesirable because it detracts from the nature of the method of being boundary only. All right, so we need to find a way. We need to come up with a way, to formulate a way of dealing with that integral on a boundary only basis. Okay? So we need to find a way of obtaining the elements of the I using a boundary only approach. All right. Luckily, some people before us, actually in the early 90s, came up with a general technique of doing this and sending all the information that's contained within the interior, because B is an interior function, right? B is interior, it's actually called internal generation for a reason. So some people found a way of actually taking that information and sending it back to the boundaries and using boundary information, boundary integration to obtain its results. All right, so let's look at how to do this. There are special forms of B. Let's call it B of X that will automatically, or almost automatically, lead to elimination of the domain integral. There's two cases. Well, there's a few, right? But two cases that come to mind immediately. One, if B of X is, what do you call it, contains concentrated sources or sinks. Those concentrated sources or sinks are infinitesimal small in scope. That means that imagine a field where you have an infinitesimally small point where energy can come in or come out. Okay? That seems far-fetched, but it can actually be modeled experimentally. It can be part of reality too. It's called a concentrated load in mechanics, and heat transfer is called concentrated source or sink. Okay? And it can be an effect of a third dimension. Remember, we're analyzing a 2D problem, and there can be something on the third dimension adding heat at a particular location that we can consider infinitesimally small, or subtracting heat at that location. In this case, B of X is modeled as a summation from k equal 1 to m of bk times d of delta x, comma xk. That's a direct delta function. That's how we model an infinitesimally small source. Okay? It's an infinitesimally small source of an infinite magnitude at that location. That when we integrate it, it becomes finite. So when we integrate that, it becomes B, right? So the magnitude of the source itself is not infinitesimally small or infinite. All those two cancel out, and they just become B, right? So that exists in mechanics. That's called a point load. When you're dealing with a mechanics problem, and then you have like a concentrated load on top of a structure, and that load is at a point. What do you do with it? That is modeled with a direct delta function. That's a point load. Okay. In heat transfer, it's called a concentrated source or sink, because if B is negative, then this is a sink. Okay, of magnitude B. So if this is the case, if B can be modeled by this, and notice again, these are direct delta functions. So recall Bi, which is B of psi I, is equal to the integral of Bx times G of x and psi, and therefore the elements Bi, psi I, the elements of Bi are equal to the summation from dk delta x comma xk, where xk are the locations of the sources, times G
This implementation of a boundary method, like would the implementation of BEM and a Poisson equation be inefficient compared to the other ones? Like, would you rather use FEM or?
No, the way we're going to be doing it, so we're trying to do, we're trying to retain everything on the boundary to make it an order of magnitude more efficient than FEM. Okay. And also for it to require less discretization than FEM, because once you go to the interior, you have more points, you have more unknowns, and so on. So it would be more efficient and more accurate. Okay? As long as we do it properly, we're going to send that information to the boundary. In this case, we don't really need to send it to the boundary, because it's already lost in here. Because the elements of Bi are an integral of B times G. And B is, or has forms of the direct delta function. So, basically we can rearrange this and make this a summation from, K equal 1 to M being the number of sources. Yeah, I forgot to say that. Such that I'm going to say it here. Xk, source location, and Bk, source strength, and M, number of sources. So here we have Bk times the integral over the domain I. All right. So now, as long as all sources xk belong to the domain, okay, as obviously the case, if you are going to say there's this many distributed sources, those sources are within the domain. So what is the answer of this? Domain integral? What is the solution here? What is the integral of any function multiplying the direct delta function?
The function.
The function evaluated at the source point of the direct delta function. So this would be simply Bi is equal to the summation over all the sources of the magnitude of each source times the Green's function evaluated at the source location at the point xi I. And remember that xi I is just simply the original source of the fundamental solution located at each of the boundary elements. So for each boundary element, we have G evaluated at all the source points and added together. And that's it, it's solved. So now we have the elements of the vector B. All right. So I guess, so at least for concentrated sources and sinks, could be sinks too again, because B could be negative. Then you have these the simple solution. No integral to be solved. No integral needed. All right. Now case number 2. If B of x is constant. All right, well, this one is not as straightforward. The elements of BI are B of psi I, which are equal to the integral over the domain of Bx, d of x and psi I, which are now just simply B times g of x and psi I d omega. We need to solve that integral, the integral of the domain of the Green's function. That's the log of R. All right, so how do we do that? Any ideas? All right, I'm gonna do it in 2D. You're gonna see how it's going to work. G of x and psi I is equal to minus 1 over 2 pi of the log of R, which is, I'm gonna write the whole thing here. So log of x minus xi squared plus y minus yi squared. All right? This is the same as saying G of R is equal to minus 1 over 2 pi log of R. All right? Now let G of R be equal to the Laplace of some function Vr that we don't know. So we're going to try to get a function V whose Laplace is equal to G. We're going to try to get a function V. When we differentiate it twice, we get the log. Right? Whatever it is. Seems easy enough. All we have to do is integrate G twice and get the log. But we are able to do that because G is a function of a single variable. Well, G is a function of x and y. But x and y in a radial only basis. That means that G is only a function of R. So we can express G in polar coordinates, and therefore we can express the Laplace in polar coordinates. Okay? So, in polar coordinates, G of R is equal to 1 over R d dr of R dv dr. That's the Laplace in polar coordinates. Whoops. I'm going to write the whole thing. The Laplace will be 1 over R squared, the second derivative with respect to theta squared of Vr but this one will go away. Because v is expected to be only a function of r. Right? So, there we go. So 1 over r d dr r dv dr is equal to minus 1 over 2 pi log of r. So what do we need? Now it became a 1D problem. All we need to do is multiply both sides by r, right? Integrate, then divide by r, then integrate again to get b, right? Multiply both sides by r, get rid of this r, integrate, get rid of this derivative, divide by r, and integrate again, and now we have b. So, integrating twice leads to br is equal to minus r squared over 8 pi log of r minus 1. And you can try it if you want. Take this, differentiate it with respect to r. We gotta integrate the product or differentiate the product. Multiply times r, differentiate with respect to r again, and divide by r, and you'll see you get the log of r. All right. Or b of x and xi is equal to minus x minus xi squared plus y minus yi squared divided by 8 pi times the log of the square root of x minus xi squared plus y minus yi squared minus 1. So notice I went back to Cartesian coordinates in 2D. So now we know what v is in 2D. We can do it in 3D too. No big deal. Now in 3D, we're talking about spherical coordinates, right? And the Laplacian spherical coordinates is going to have an r square here, and it's going to have an r square here. So the integration is going to be slightly different. And the theta, the azimuthal and equatorial components, they go away. All right. So now we have a b of xi I, which is equal to b times the integral of g of x and xi is equal to b times the integral of b of x and xi d omega. And we know what that function b is. So what good does it do? What can we do with a domain integral that has not a Laplace, but a divergency? Remember that the Laplace is the divergency of the gradient of v. It's del dot grad v. Del dot del v. We use the Gauss divergency theorem to turn any domain integral into a boundary integral. We use Gauss divergency theorem to turn the domain integral into a boundary integral. And therefore, the elements of vi, which are the elements of v of xi I, are equal to b times the integral over the boundary of dv dn d gamma. And now we've translated all the information that was on the interior. Well, granted that it was constant information, we moved it to the boundaries, okay? In the form of this function b multiplied times b. So now we use, I'm gonna frame this one, the same discretization into n supramatric boundary elements, and therefore bi should be equal to b times the summation from j equal 1 to n of the integral over delta gamma j of dv dn of x psi I d gamma, and we're going to call this, each one of these, we're going to call u ij. So bi is equal to b times the summation from j equal 1 to n uij, such that I goes from 1 to n. And that's it. Now all the information is on the boundary, and the boundary integral is solved the same exact way we solved all the other boundary integrals for g and h, for which we already have the structure in the code. We already have the mechanism, we already have the integration routine, we already have the discretization. We don't need to do anything else, okay? You just create a separate routine, and that separate routine is just going to call another fundamental solution, which is this v, which is that r squared over 8i and so on. Its normal derivative is very easy to find, just differentiate with respect to x and differentiate with respect to y, times the normal vector, which you already know how to calculate because we do that for h, right? And find those elements, and those are each of the elements that go on the right-hand side of the discretized boundary integral equation. Okay, so plug into H T G Q plus B and so on. And that's it. And again, that's how we solve the other special case, which covers a wide gamut of cases, because more often than none, if there is a generation term, that generation term is going to be constant, like a distributed resistor over the domain or something like that that generates electricity, or some sort of chemical reaction that's taking place within the conducting domain that generates heat or energy. Okay, and in some very specific cases, the generation will be space dependent. But if the generation is constant, it is as easy as doing this, okay? Now next Thursday, we're gonna see what we do when the generation is not constant. And that will help us actually cover a much wider range of problems, not only this Poisson-like problems, but other problems in which we can send information over to the right-hand side and treat it as a generation, okay? There are other problems in which there's stuff on the equation that we don't know how to handle, and then we can actually send it over to the right-hand side, treat it as a known quantity, although it's not known, it might be a function of temperature, assume what it is, treat it as a space-dependent generation, solve the problem, and iterate back and forth until we get the right answer. All right? Are there any questions? All right, so we'll see each other on Thursday. Remember, that would be the last time we'll see each other before spring break. And the project is due right after spring break. Well, Thursday after spring break. So make sure you bring questions on Thursday so we can address them, okay? See you then.
Sí, la proyecto cuando quería compilar el proyecto.